Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So good evening, students. So today we are going to start a new chapter, coordination compounds. In this chapter, we will mostly be studying about the coordination compounds and the name, as you see the name of this kind of specific kind of compounds, the coordination compounds. From name itself, it is clear that this compound will contain some coordination bonds. And the coordination bonds, if you remember, we have studied it in covalent, chemical bonding. So three types of bonds mostly we have seen: ionic bond, covalent bond, and the coordination bond. So coordination bond is a special kind of bond when share pair of electrons, means both the electrons of the shared pair are donated by one particular atom or a group of atoms, which could be a molecule or could be a polyatomic anion as well. But it will be donated by one particular atom only of this polyatomic anion or molecule, or even if it is monoatomic anion, it will be only one atom which will be donating both the electrons that are taking part in the co- covalent bonding. So coordination compounds, the coordination bonding, coordinate bond is a special kind of a special kind of covalent bond only. So sharing happens, but a sharing that sharing is a donation, or not donation, but sharing happens from only one atom, and another atom has a vacant orbital. So one atom has a complete filled orbital, which could be because of the presence of a negative charge or maybe presence of lone pair on it, and another atom which is an empty orbital. So a fully filled orbital will overlap with an empty orbital, and so such bonds will be formed. So here is what we know, the coordinate bond. So let us look into, and these coordination compounds have lots of applications in many areas of chemistry as well as biology. If you remember, there are lot many enzymes are there which they contain coordination compounds as in the active site. For example, if you look at the hemoglobin, it contains heme part and where the iron resides in it, and that is what we call the porphyrin ring. And with iron is called the heme part, and this is what we see. And this is the active part where the oxygen coordinate to the iron atom, and so that is how it gets carried from lung to the tissues of the cell. And another important application in chemistry is in catalysis. So it is the coordination compounds, lots of coordination compounds, particularly organometallic compounds, are used as a catalyst, a particularly homogeneous catalyst. And what are the homogeneous and heterogeneous catalysts? Example, we have these definitions we have already seen with examples. Homogeneous means the catalyst as well as the reactants are in the same phase. They are in the solution phase or some other phase. So coordination compounds, when they are used mostly as a catalyst, they will be mostly working as a homogeneous catalyst. Let us look into the chapter outline, what we will be studying, what we will be discussing in this chapter mostly. So first of all, we will be studying about the postulates of Werner theory of coordination compound. So what is the Werner's theory? Werner was a scientist, and he for the first time described about the some basic nature of coordination compounds, and some of the common definitions he also gave. Those things we will see with his postulates and some other common definitions in Werner's theory of coordination compounds. Then we'll also see the definition of some very common terms. Some of the terms we'll already see here, and some other terms we also see. So there's a coordination entity. This coordination entity, you should have the idea. Coordination entity means it constitutes a metal ion, or this metal could be even in the neutral oxidation state or zero oxidation state, or it can be in a positive oxidation state, means in the ionic form. And this metal ion will be bound by some other ions or the counter ions or maybe some neutral molecules, and that is the entire thing is constitute. This is called coordination entity. So metal ions, when it is bound coordinated by some ions, some other type of ions, mm, opposite ions or maybe some neutral species, this entire thing is called coordination entity. And in that coordination entity, what we see, there is a central atom. So the atom which is bound to many different entities which are called a ligands. So many neutral molecules or maybe some other ions, monoatomic or polyatomic ions, it is bound to, and each coordination compound, usually the number of these eight ions or the ligands that we call, their number are fixed. And that is what we see, we'll see in the such things in the Warner's theory as well. And the number of these ions are called what is called coordination number. And Warner's theory, Warner said this as a secondary valency. The same thing, the coordination number that we call was Warner said this as a secondary valency. Then we looked into the denticity and hepticity of ligand. So ligand, we have seen ligand is something which is bound to the central metal. Central metal means there is a metal, and there are many things which is bound in different directions in a given orientation and along different axes, and those are two different molecules or ions. Those are ligands, and the central metal is what we call, that is already clear. So coordination entity contains central atom as well as ions or ligands. Then once we know the ligand, what is ligand, then we also talk about the denticity and hepticity of a ligand. So denticity is, it calls how particularly how many bonds a ligand can form with the central metal. If a metal forms only one bond through one atom with a metal, then we call its denticity is one, and so we call it the ligand is monodentate. If it can form two ligands, for example, ammonia. Ammonia is a monodentate ligand because bound, it can bind to a central metal only through one nitrogen atom, and so it's a monodentate ligand. Water is also a monodentate ligand. Chloride ion is also a monodentate ligand. And then we talk about the bidentate ligand. If the two atoms are of a ligand bound to a metal, so that kind of ligand is called bidentate ligand. And for, if you look at the example, diethylamine, so ethylene diamine. Sorry. So ethylene diamine, if you look at, this is called this is NH2 CH2 CH2 NH2. So both NH2 groups will now coordinate with the metal, and so it can form two bonds with the metal, and so we will call it as a bidentate ligand. And there are many ligands which can form many bonds with the metal. For example, if you look at EDTA, ethylene diamine tetraacetate, it can form six bonds it can form up to six bonds with a metal, and so it is a polydentate ligand. So monodentate, bidentate, then we talk about the polydentate ligand. We also talk about ambidentate ligand. So if a ligand is there and it has two atoms, which in that ligand which can bond, any of which can bind to a metal, then we call them ligand is a bidentate ligand. For example, if you look SCN minus, SCN minus is ligand SCN minus thiocyanate ion can bound to a metal through sulfur atom or nitrogen atom. So it has potential to bound through both nitrogen and sulfur. In some of the coordination compounds, it will bind to sulfur, and in some of them it will bind to nitrogen. And so such ligands are called ambidentate ligands. Then we also talk about the hepticity, and based on this ligation, we also see different ligands also have the capacity. It may bond if the ligand is a bidentate or polydentate ligand. It may be that the coordination compounds may be polynuclear. It's not only the mononuclear. It means it can this ligand can bind to one of the person with one person to a one to one metal, and through another person it may bound to some other metal, and such we see the bridged ligands we also see. And usually bridging we see in the case of the multi-heptate ligand. And the hepticity we also define. Hepticity, the difference is hepticity and tenticity we see in details later on. Basically the difference is in hepticity we see there is a continuous, either there is a conjugation between the bonded atoms. So hepticity means if the hepticity is one monoheptic ligand, it means it will form only one bond with the metal. And if the hepticity is two, there's a biheptic or the diheptic ligand. So it will form two bonds with the metal. So two atoms will be coordinating, of ligand will be coordinating to the metal. So usually what happens in hepticity and denticity, the difference is that the bounded or the coordinated atoms of the ligands are, they are continuous in multi-heptic ligands. However, in the case of multi-dentate ligands or polydentate ligands, we see these atoms are not linked, they are not in the conjugation, or they are not in continuation. So there is some breaking in the continuation that we see usually. For example, as I said, NH2, CH2, CH2, NH2. So these two NH2 which are binding to a metal in this bidentate ligand, they are separated by two CH2 groups. But the hepticity, if you look at the hepticity, usually see we see like if you look at the uh, uh, there are many ligands like that. For example, if I look at this allylic anion. So allylic anion CH2 double bond CH2 single bond CH2 minus. So we can see the hepticity in case this ligand can bound to a metal only through CH2 minus the carbon which contains the negative charge, or it can bound to another two atoms as well. So this carbon CH2 minus then CH2 CH2. So it can be a monoheptic or triheptic. So of all the three now other CH2, CH2, these two means through pi bond, these two carbon atoms can also bind to a metal. And so we see all the atoms are in continuation CH2, 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 and so this will be called triheptic ligand. So this is how the hepticity will decide, and a difference we also I have just explained. Although you may not be understanding about what exactly the ligand is and other definitions in details, we'll see everything later on about everything in the later part of this lecture or maybe in the next lecture, so depending on the time. Then we will also see about the coordination number, and the coordination number I have already explained. So how many anions or ions or the neutral molecules in all together are bound to the central metal is called coordination number, and the coordination sphere. So what we see, the coordination entity is also can also be called as coordination sphere. Usually now we call it as a coordination sphere. Then we see the coordination polyhedron. So as you know, how many ions, anions or cations of the neutral molecule are bound to the central metal, and what will be its structure. Usually, the geometry of it is called coordination polyhedron. Usually, if you remember the VSCPR theory, we determine geometry based on the hybridization and other factors. So here also we take help of the hybridization to determine the geometry of the transition metal complexes, and there we see the, and that is what we look into the coordination polyhedron, so what shape it will form, and that is what. And then the oxidation number. What is the oxidation number for any atom of metal? This thing we have seen in details in the redox chemistry, that chapter that is dedicated to redox chemistry. And the oxidation number will see what exactly the what will be the formal charge usually on that this metal, means where the electrons will be transferred from metal to the ligand or ligand to the metal. There are many two ways basically to find out the oxidation number, and what ways you will we will follow this in details in the coordination compounds to find out the oxidation number. There are certain rules. Those rules we will be mostly studying about. The coordination of the oxidation number, that then formal definition we know. We have already seen it earlier. Then we'll also see about the homoleptic definition of homoleptic and heteroleptic complexes. Homoleptic means if all the ligands are same, such complexes are called homoleptic complexes, like hexaequiron complex or hexaamino iron cobalt complex. So this kind of complexes are, if all the ligands are same, such complexes are called homoleptic complexes, and if all the ligands are not same, such complexes are called heteroleptic complexes. Then we'll see the nomenclature of coordination compounds, and the nomenclature of coordination compounds. There are many things that we have to study. Some rules we will study. What are the rules that we need to follow to name to write the IUPAC name of a coordination compound, and these rules are given by IUPAC, as we have seen this name IUPAC name of organic compound. So similar kind of some rules we will see there as well. Although their naming of our coordination compounds are much different than the naming that we follow in the in the case of organic compounds. Usually here we see the ligands. If the ligand is anionic, it will be named differently. Differently, if the ligand is neutral, it will be named differently. If the metal ion is in the coordination sphere, it will be named differently. Means if in the coordination sphere metal and will be in the coordination sphere. But if this coordination sphere has a positive charge or it is neutral, then it will be named differently, or if it is having a negative charge on it, then it will also be named, it will be named differently. So based on that, we will see what rules we will follow for the IUPAC nomenclature of coordination compounds. These things we will also see. Then we will see formulas and names of mononuclear coordination compounds. Mononuclear coordination compounds means this coordination compound will contain only one metal ion, and this metal ion could be the transition metal or inner transition metal or some of the main group metal it can also contain. Some of the coordination compounds are, are formed by main group elements, like magnesium can also form coordination complexes and so on. Or the lithium can also form coordination complexes. These kind of examples we'll see later on if it is required. Then we'll see the isomerism in coordination compounds, like we have seen isomerism in the case of organic chemistry. So there we show two kinds of isomerism, the structural isomerism and stereoisomerism. Similarly, here we will also see structural isomerism and stereoisomerism. In the organic chemistry, we have seen optical isomerism and geometrical isomerism as a part of stereoisomerism. The stereoisomerism could be of the optical isomerism or the geometrical isomerism. Here also stereoisomerism could be optical isomerism or the geometrical isomerism, and the ideas behind them are also similar here, almost same. However, the structural isomerism can be different here than that we have seen in the case of organic compounds. Here we will see mostly the structural isomerism as well as the linkage isomerism. If the linking is different, if the ambidentate ligand is there, and if in the case of ambidentate ligand, in one of the complexes, some one atom is forming, making bonds with the metal ion, and in another complex, the other atom can also form a coordinate bond with the metal, like I think Hn minus. In one complex, suppose metal ion is same, everything is same, other than in one of the complexes, sulfur is coordinated to the metal ion, and another complex, nitrogen is coordinated to metal ion. So we'll see the linkage isomerism. Then we also see the solvation isomerism. Solvent, the number of solvent molecules taking part in the coordinate taking part in the coordinate bond formation is will be considered here, and so we say the solvent isomerism. So there are some types of structural isomerism, mostly four types of structural isomerism we will see in this case. Then we will talk about the nature of bonding in coordination compounds. Like we have seen mostly the valence bond theory we have seen in the chemical bonding itself. So valence bond theory we will also see, and the valence bond theory we have seen for any organic inorganic compound. It we take the help of valence bond theory to find out the geometry of an organic or inorganic compound. Similarly, we will also use valence bond theory to find out the geometry of the coordination complexes. And then we'll also later we'll see that the two types of complexes, a high spin complexes and low spin complexes, based on the concepts of the valence bond theory. And then we move to the crystal field theory, and in the crystal field theory we will see how d orbitals of the metal it splits into the crystal field, and because of the splitting of these orbitals we will see some kind of gap is created between some different degenerate d orbitals. So usually dxy, dyz, dzx they go together, and dx square minus y square and dz square they come together, and so these are different degenerate orbitals. So we will see the crystal field splitting of these orbitals, and based on the crystal field splitting and also the pairing energy, we'll see how much this stabilization will be there. And another point of the valence bond theory, based on the valence bond theory, we can also find out the magnetic properties of complex compounds. So magnetic properties, particularly paramagnetism and also the magnetic moment of complex compounds, we can calculate based on the number of unpaired electrons. We will count from the valence bond theory with the high spin and low spin complex. Similar kind of things we also see with the help of crystal field theory, and the low and high spin complexes can easily be understood when we resort to crystal field theory. And once we study that the crystal field in the in the ligand field in the field of the ligand, the d orbitals of the metals are splitted, and because of the splitting you will see two levels of d orbitals are formed, and if the electron is there in the d orbitals, so there are transition of these electrons from between these two orbitals can also happen, and this transition can also lead to, if it is in the visible range, it can also lead to the color to the coordination compound, and that we call the DD transition. The region of the color in the compounds is DD transition, and those things you will see. Particularly, if you remember potassium dichromate, its color yellow color is because of the DD transition and so on. And then the significance of and applications of coordination compounds in day-to-day life will be discussed. So these are the basic outline of this entire chapter and which we will be studying. Let us first come to the introduction of this chapter. So the transition metals usually form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules. So to remember here, this transition metal is actually the metal is bound to a number of anions, or it can also bound to a number of neutral molecules, or it can bound to some number of anions and some number of neutral molecules by sharing electrons, and these electrons will be shared by only one entity, one chemical moiety, and so one can consider as a coordinate bond, and so the coordination compounds will be formed. You please remember that the usually transition metal forms their coordination compounds of transition metals are more common. It doesn't mean inner transition metals, means the lanthanides and actinides will not form coordination compounds, or even main group elements will not form coordination compounds. Usually to form a coordination compound, the charge of the metal should be high and its size should be smaller, and there should be high charge size density, and so we will see this metal ion is suitable to form complex, and also the metal ion should have a decent size so that it can bind to a significant number of ligands, so that because of that binding there will be a stability to this entire system. And so these kind of things, and what is the criteria for the formation of coordination compounds, those things we will see later on. So, but here you have to remember, mostly transition metals form coordination compounds. It doesn't mean that the other metals will not form coordination compounds. So the other group elements can also form coordination compounds, although they form very rarely, and very few elements of other groups form coordination compounds, the stable coordination compounds. So the chemistry of coordination compound is an important and challenging area of modern inorganic chemistry. And why it is challenging and important, its importance is particularly because of the catalysis. Now these coordination compounds, particularly one kind of coordination compounds are called organometallic compounds. They are used now as a catalyst, homogeneous catalyst, and so this kind of this chemistry is very challenging and important. Their application is also there in some other area, like suppose there is some kind of heavy metal poisoning happens to some certain person. So what can we do? We can use certain ligand which can make a very strong bond to this metal, and once this metal forms, the complex its property will differ. It will having a different property, and so its toxicity may go down. Or maybe once it forms the complex, it may become soluble in water, and so it will come out to the excretion. So these kind of things one can use in even the medicine, and also there are many applications of this coordination compound, which one of and some of which we will see later on the last page of this chapter, particularly last lecture of this chapter. So, like for example, if you look at the coordination compounds are vital components of biological systems. For example, the chlorophyll, it contains magnesium, and as you see here, the main group element is forming in the complex compound. So the chlorophyll, also they will see a porphyrin ring in that case. And what is the structure of porphyrin ring, that we'll see later on. So the porphyrin term, you should remember the porphyrin ring. The structure and other things we will see. Although we will not see the structure of chlorophyll, or hemoglobin or vitamin B12, the example that are shown here, because it is not in your syllabus, it's beyond the scope of this chapter. So, or your syllabus, and so will not see in details the structure of this compound, but you should understand that the chlorophyll very important pigment for the photosynthesis. If chlorophyll is not there in plants, the photosynthesis will not happen. And if photosynthesis doesn't happen, so what will even we cannot survive, because we are mostly indirectly or directly dependent on the plants for our food. So there will be no life on Earth if chlorophyll is not there and if it doesn't contain iron. This chlorophyll contains magnesium ion, and so you can see the importance of coordination compounds. Then hemoglobin. Our survival is based on the respiration or based on the hemoglobin which carries oxygen from lungs to the tissues. And the hemoglobin also contains porphyrin ring which is coordinated added to iron. In the center of the porphyrin, the iron atom is coordinated, and so what we see the presence of iron. This is also a coordination compounds in the hemoglobin. Vitamin B12, it contains cobalt, and so this kind of the importance of these compounds you can see there are many enzymes as well which contains in its active site contains coordination complexes or coordination compounds. For example, cytochrome P450, it also has porphyrin ring, and there the iron metal is there in different oxidation states. And so this can also contains there are many enzymes which contains copper, molybdenum as a and its active site of copper, molybdenum, and some other sometimes manganese, some other metals, iron, magnesium, and this kind of things we have already seen in the active site of those enzymes. And if you remove these metals or this coordination compounds from that active site, the catalysis will not happen. The enzyme will become inactive. It will not function. And so you can see the importance again importance of organometallic compounds in our survival. So variety of metallurgical processes, industrial catalysts, and analytical reagents involve the use of coordination compounds. Some of the examples we will see later on. Coordination compounds also find application in electroplating, textile dyeing, and medicinal chemistry. And what are these? Some with certain examples we will see everything later on. The central atom or ion, usually metallic. So central atom or ion, which is usually metallic, of a coordination complex is called coordination center. So this is what we so the central atom or the metal or the ion, which is bound to different ligands or different mm, uh, anions or neutral molecules is called coordination center. So central atom or ion of a coordination complex is called coordination center, and the bound molecules or ions to the coordination center are called ligands or complexing agents. So the ligands for the central atom which forms forms bond to many other elements or the ions or the neutral molecules are called coordination center, and the metals or sorry the ions or the neutral molecules which forms different bonds which forms bond with the central metal or the coordination center are called ligands or complex agents. And what does it mean? For example, if you look at this complex, if you see this FeCN6 4 minus, so here iron Fe is the coordination center, and Cn minus 6 Cn minus each Cn minus ions are called ligands in this case. So coordinate bonds link the central metal atom or ion with the ligands in this compound, which I have already explained. So please note that both double salts and coordination compounds, so there are two terms where sometimes we get confused. What does it mean? For example, if you see this molecular structure of these molecules appears quite close to this. So some people may get confused that this compound may also be a coordination complex, but it is not. It is a double salt. So there are two terms that sometimes makes confusion, and so we should know what is the difference between them. So please note that the double salts and coordination compounds are formed by combining two or more stable compounds in the stoichiometric ratio. So when two or more stable compounds uh, when they react or when they combine in a stoichiometric ratio, they can either form double salt or the coordination compound. So what is the difference between them? However, double salts such as the examples are there carnallite, it is potassium, magnesium chloride, Moha salt, ferrous ammonium sulfate, and some water of crystallization is there. And the potash alum, we also the alum in Hindi we call it fitkiri. And so this is also a double salt. So these are examples of double salt. This is potassium aluminum sulfate, or you can call potassium sulfate aluminum sulfate and 24H2. This is ferrous sulfate ammonium sulfate 6H2. Commonly we call ferrous ammonium sulfate, potassium magnesium chloride or potassium chloride, magnesium chloride 6H2. These are double salts, and these double salts dissociates into simple ions completely when dissolved in water. What does it mean? It means that when it dissolve this compound into water, you will see you can detect the presence of K plus ion, potassium ion into the solution, presence of magnesium ions into the solution, as well as presence of chloride ions into the solution. When you dissolve more salt, you will see the presence of, you can detect with certain techniques, presence of Fe2 plus ion, a ferrous ion, or the presence of ammonium ion, or presence of sulfate ions in the solution. Similarly, in the case of potassium, when it is dissolved in water, it can give the taste of potassium ion, aluminum ion, and sulfate ions, each ions. However, in the case of complex ions, each this complex ion will not be dissociated into all the ions that forms this complex. We can only test for the presence of certain ions. For example, but complex ions do not dissociate into corresponding ions on dissolution in water. For example, if you look at this ferrocyanide, FeCN6 4 minus of potassium ferrocyanide. So this ion, if it was a if it was a double salt, it should be broken into potassium ion, cyanide ion, and Fe2 plus ions. However, what we see, this complex it dissociates only into K plus ions and this ferrocyanate ion. So we cannot detect the presence of Fe2 plus ion and Cn minus ions into the solution. So it will not be broken into Fe2 plus ion, ferrous ion, and standard ions. And so this is what we call the complex ion. The complex ion is FeCN minus FeCN6 4 minus ion will not be dissociated into ferrous ions and the cyanide ions. And so it is what we call complex ion. It is not the double salt or the complex compound. And in this complex compound, we can test get a taste in its aqueous solution. Presence of K plus ion or you can just test for the presence of FeCN6 4 minus ions. You cannot separate this Fe2 plus ions and Cn minus ions in aqueous solution on dissolution. Let us now look into the Werner's theory. And the Werner's theory, as I said earlier, is a very important first systematic study about the complex compounds, and many of the ideas that we still use today was given by Werner. So Werner, a Swiss chemist, prepared and studied several coordination compounds, and in 1898 he propounded his theory of coordination compounds, and the main postulates of the Werner theory or the Werner's theory is as given here. So in coordination compounds, metals show two types of linkages. So what he said, metals show two types of linkages, and these linkages can be called valencies, and these valencies, two types of linkages or valencies are called. He defined, we gave two terms, primary valency and secondary valency. So if you see this complex compound, you see this metal, iron, has bound to the Cn minus and one valency, then see it will also bound to this potassium and this complex non into the aqueous solution. And so two valencies you can see in this case. So primary valency and the secondary valency. He said the primary valencies are usually ionizable and are satisfied by negative ions, depending whether negative ion or positive ion. So what the primary valencies are usually, it will be ionizable. So if you dissolve this into water, you can see the potassium ion will be ionized. This complex compound will be ionized into potassium ions and the ferrocyanide ions. So this is the primary valency which will be ionizable. However, there is another valency that is between the bonding between iron and Cn minus ions, and that is not ionizable. So what we see, the primary valency as two kinds of linkages or valency. So there is a linkage between iron and cyanide ion. This is what we defined as the secondary valency, and secondary valency is not non-ionizable. So the primary valencies are usually ionizable and are satisfied by, you can say, counter ions or the opposite ions. Negative ions, here it is written, it means if the coordination sphere or the metal, the complex ion contains a positive charge on it. So actually his study is based on this kind of ions only. So he said in that case, for example, if you look at this complex, you see this complex compound, the complex ion contains a positive charge. So there is a negative charge, and this negative charge, this is called this one Cl minus ion, and this is called the primary valency. The primary valency of this coordination compound will be 1 in this case, and the secondary valency will be what? The 2 Cl minus ions and 4 NH3 molecules. So secondary valency will be 4, and these bonds are not easily broken when this compound is dissolved in water. So secondary valencies are non-ionizable These are satisfied by neutral molecules or negative ions. In this case, you see, it can be satisfied secondary valency by a neutral molecule like ammonia, or in this example, or the ions, the chloride ion, as you can see in this case. So the secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions. The examples we have already seen. The neutral molecules or the negative ions here. Again, the secondary valency is fulfilled by the negative ions in this case. In this example, potassium ferrocyanide, not cyanide, sorry. So the secondary valency equals the coordination number and is fixed for a metal. So the secondary valency can also be called coordination number, and this is fixed for a metal almost. Usually, this is what he said. However, it may not be necessary depending on, now people know, depending on the size of the ligand, you can also play with the coordination number of the central metal. So the coordination number of the secondary valence is also depends on how much space is available around the metal. So that how many ligands, with how many ligands it can actually form is what it also depends on the space around it. So what he proposes that it is usually fixed for a metal. Later on, today we see that this is not a necessary criteria for a coordination compound, but this was just a first study of coordination compounds. I read that too around 1898 he published his work, and so it is too early. And even at that time, we had no idea about chemical bonding, coordination bonding, and anything. We had no idea about that. There was no concept of chemical bonding at that time. And the ions groups bound by secondary linkages to the metal have characteristic spatial arrangement corresponding to different coordination numbers. What does it mean? So characteristic spatial arrangement we said is there, and we will also see this thing will be talking when we will see the valence bond theory. So what will be their spatial arrangement of different ions or the cation, the ligands around the metal, and their spatial arrangement, the geometry will talk about later on, like the coordination polyhedron, we'll talk about the coordination polyhedron later on. In modern formulation, such spatial arrangements are called coordination polyhedron, as I just said. The species within the square brackets are coordination entities. So usually the coordination entities or the coordination complexes are stored in square bracket. And now these are also called coordination sphere. So coordination entity and coordination sphere are seen. And the ions outside the square bracket are called counter ions. And so as you see this, usually when we see this is FeCN6 4 minus. So FeCN6 4 minus, and if you write K4 here. So the species, all everything that is written within the square bracket, this square bracket is called coordination entity or coordination sphere. And this coordination entity or coordination sphere will contain metal ions, central metal, as well as some anions or the neutral species. So these species within a square bracket are coordination entities or complexes, and the ions outside the square bracket are called counter ions. And in this example, you see the potassium ion is what? The counter ion. In another example, if you see this in this case, what we see, this is the species which is in the square bracket. So this is called the coordination sphere or the coordination entity, and this coordination entity contains this cobalt metal in its plus 3 oxidation state, and which is a central ion, and this negative ligand, negatively charged ligand is Cl, 2 Cl minus ions, 2 chloride ions, and 4 ammonia molecules. And these ammonia molecules and the chloride ions are called the ligands in this case. So the different definitions that we have I have just briefly mentioned earlier, we can see here with this structure. So yes, in this structure, what we see, the entire thing, this is called coordination sphere, or Werner said it's a coordination entity. And this coordination sphere usually contains the complex ion or the complex center. And some counter ion, if this has certain charge, so you can see that some counter ion will also be there. If this coordination sphere is electrically neutral, so there will be no counter ion in that case, because to have a counter ion, there should be certain ion on the coordination sphere. About if it is cationic, so the counter ion will be anion, and if it is anionic, the counter ion will be cation. And then in that case, we have seen this is the anionic coordination ion or the complex ion, So in that case, the counter ion is potassium. This is a cation. And now this is a central metal, and this is a central ion metal, which is the ionic form. It has a certain charge on it, so it is central metal or central ion. And this central metal, in this case, you can see it has its oxidation number is +3, and that +3 is actually balanced by two chloride ions that are there in the coordination sphere, and one chloride ion which is outside the coordination sphere. And so, since only one chloride ion is outside the coordination sphere, so this is called primary valency. So primary valency of this coordination complex is 1 because it has only one chloride ion as a counter ion. And now one chloride ion as a primary valency, two chloride ions as a secondary valency. So three chloride ions will have three negative charge. And so those negative charge, because the entire complex does not carry any charge, it is electrically neutral, the cobalt must be having +3 charge on it. And that is what we call in this case is the oxidation state of the central ion or central metal. Now this ammonia molecules, four ammonia molecules, this ammonia, each nitrogen of each ammonia molecule forms a bond with the cobalt. Similarly, both the chloride ions forms bond with this cobalt. And so these are called, this is a center ion because it is center, and sometimes two chloride ions will come from two different directions and four ammonia ions will come from other directions. And so the cobalt will be in center in the middle, and these different uh, this four ammonia molecules and two chloride ions will come from different directions and uh, will bind to this metal, and so these are called ligands, and this is the central ion. And this, as we saw, this primary valency, it is ionizable. However, the secondary valency or the coordinate, something which is there in the coordination sphere, is not ionizable on resolution in water. And so the coordination number or the primary valency in this case is 1, or the second, and the secondary valency is 2 chloride ions and 4 ammonia molecules. So 4 plus 2, 6. So the secondary valency of this complex is 6, and that secondary valency is also, as I have said earlier, is called coordination number now. So the coordination number of the cobalt is in this complex is 6. Nowadays, what you can see coordination number, a general definition of coordination number is how many atoms are in direct contact with the metal is called coordination number. Coordination number, the same definition you remember is also there in the, we have seen this in the case of in the chapter solid state. In the solid state, if you look at the crystals, how many atoms have directly come into contact, atoms or ions are in direct contact to the given ion is called the coordination number. Given ion or given atom is called coordination number. So here as well. So how many atoms are directly linked to or in direct contact to the cobalt or the central metal or central ion is called coordination number. And you can see two chloride ions will form a bond with the cobalt, and four ammonia molecules through nitrogen will form bond. So the nitrogen, four nitrogen atoms will be in direct contact with the cobalt. And so 4 plus 2 is what? 6 is the coordination number of this complex. So if you look at this primary valency, the binary compounds such as chromium chloride, chromium 3 chloride, cobalt 2 chloride, or PDCl2, palladium 2 chloride, have primary valency. They are all these binary compounds containing only two elements. They have valencies. In this case, the primary valency is plus is 3. In this case, primary valency is 2, and this case, primary valency is also 2. In the series of compounds of cobalt 3 chloride with ammonia that we see, this cobalt 3 chloride with ammonia, it was found that only some of the chloride ions could be precipitated at its AgCl by adding excess silver nitrate solution in the coal. And this experiment was actually done by Werner, and based on that, actually he came to this all the postulates that he has given. What he saw is he saw the yellow cobalt 3 chloride and with ammonia. When he saw this compound which is yellow in color, it gives three molecules of AgCl. So when if you dissolve this compound in water and then you add silver nitrate to it, so he saw that three molecules or 3 moles per mole of this cobalt chloride, hexaamino cobalt chloride complex, which is yellow in color, it gives 3 moles of AgCl. What does it mean? It means that all the three chloride ions must be ionizable. If all the three chloride ions that are there, if they are not ionizable, they will not react with the Ag plus ions of Ag silver nitrate which is there into the aqueous solution, they will not be available if only two chloride ions is free or ionizable, and if one is bound strongly, so you can see the formation of only 2 moles of AgCl. And so based on that, he actually talked about the primary and secondary valency. So if you see this complex, so COCl3 yellow in color, it gives 3 moles of AgCl. The 1 mole of COCl3 5NH3, this is purple in color, it gave 2 moles of AgCl. However, it also contains 3 Cl3 ions in this complex. Per molecule of this complex contains 3 chloride ions. However, what Werner found that when AgNO3 is added to the aqueous solution of this complex, only 2 moles of AgCl is formed. And when 1 mole of COCl3 4NH3, which is green in color, is now to the its solution, to aqueous solution, if silver nitrate is added, it gives only 1 mole of AgCl. It gave only 1 mole of AgCl. And similarly, the another complex we found with the same molecular formula but with different color, and it also gives only 1 mole of AgCl when it reacts with aqueous AgNO3. So what does it mean? It mean here two things. Another thing that we see the same molecular formula but different color. Different colors means there must be having they are having different properties, and this different properties simply means they must be having different structure or something else must be different in the these two case of these two compounds. I mean, there are two different compounds, although their molecular formula is same, but they are two different compounds. And here also you see the formation presence of isomers in the case of coordination compounds. So having same molecular formula but having different properties of these two compounds means there are two different compounds. That is why we see different properties. And at least in the color case of color we see here, although this property, chemical property, the reaction with the AgNO3 is not different because both give only 1 mole of AgCl. It means only one chloride ion out of the 3 chloride ions that are here in this complex is ionizable. And those ionizable chloride ions one can consider as a primary valence, this is what Werner said. And the other chloride ions which are there, which are not going into form AgCl, it means those chloride ions are there very strongly bound, and that is what he said. It means it must be there in the secondary valency, it must be satisfying the secondary valency of the cobalt ion, cobalt 3 ion. So in series of compounds of cobalt 3 chloride with ammonia, it was found that so Werner found that only some of the chloride ions could be precipitated as AgCl by adding excess silver nitrate solution in the coal. And these observations, together with the results of conductivity measurements in solution, can be explained if so. There is another thing that one can, at that time it was very common, and even today we do this conductivity measurement. And as we know, conductivity depends on the number of ions into the solution. So if one molecule is ionized into 4 ions, so the conductivity will be according to the 4 ions, the ionizable ions. And suppose if one molecule is ionized into 3 ions, so its conductivity will be less because only 3 ions are free in this case. And if the molecular formula is same and only 3 ions are free in this case, it means some of the ion is heavier in this case, and so its mobility will also be uh, less because of its heavier uh, size or heavy weight, and so the conductivity will also be different. And it means that if you measure the conductivity of these different compounds, what we'll see conductivity of this complex or this compound will be maximum because it will be dissociating into 4 different ions, 3 chloride ions and cobalt NH3 hexaamine cobalt complex, and 3 chloride ions, 3 chloride ions and cobalt hexaamine 3 plus ion, and that is means one ion the coordinate complex ion and 3 chloride ions. So 4 ions will be available, and so 4 ions will be moving in the electric field under a given under an applied potential, and so the conductivity in this case will be more if the same amount of all the compounds are taken. In the case of this complex, the purple complex, and this purple complex, we see two molecules of or 2 chloride ions are ionizable. So 2 chloride ions plus one complex ion. So 3 ions will be formed. In this case, two cases, one complex ion and only one chloride ions will be formed on dissolution in water, and so the conductivity will be according to the only two ions that will be formed after dissolution in these cases. So these observations based on the how many AgCl, how many moles of AgCl is precipitated per mole of the complex, as well as the conductivity measurement. So how the conductivity is different in these cases. These solutions, these experiments can be explained if the six groups in all, either chloride ion or ammonia molecules or both, remain bonded to the cobalt ion during the reaction. So if you just consider the coordination, the secondary coordination is here. The so four chemical moieties are bound to the cobalt, and then you can see that easily explain these two phenomena, conductivity as well as this precipitation of formation of precipitates of AgCl. If you see in this case, the cobalt has secondary valency is 6, and that all the six valency is satisfied by and which is a constant by the ammonia molecule. So CONH3 whole 6, and then 3, and this complex, the coordination ion, the complex ion will have coordinate ion will have 3 plus charge, and those 3 plus charge will be balanced by 3 Cl minus ions in the primary valency as a primary valency. So Cl3 minus ion, and that is what one can see. So 3 Cl minus ion will be available now in this case. In the second case, if you see only 5 ammonia molecules are there, and since we know cobalt contains, it can form its secondary valency or the coordination number is 6, it is fixed. So what will happen? One chloride ion will go into the coordination sphere, and so only two chloride ions will be will be available as a counter ion. So the complex ion will contain, so the coordination sphere will contain CO, Cl, NH3 whole 5. So total 6 moieties, chemical moieties are there in the coordination sphere. And now only two chloride ions are available. They are free and they will be there in the coordination sphere. And the molecule will be again neutral, because even if the ion, the chloride ion is in the coordination sphere, uh, it will neutralize one positive charge of the on the cobalt. Now, in the third case or third and fourth cases, if you see, only four ammonia molecules are there in both the cases. So four ammonia molecules, and since its coordination number of cobalt in this compound is also 6, so what we see, it requires two chloride ions into the coordination sphere. So what is the complex is actually COCl2 NH3 whole 4, and now the two chloride ions in the coordination sphere. So only one chloride ion is free available, which will be there in the there as a primary valency or as a counter ion, and that is what it will, when once it dissociates, it will be dissociates into one chloride ion and one complex ion. Only these two complexes will dissociate into that, and so we'll see the formation of only 2 moles of ions per mole of this complex. However, in this case, we see 3 more formation of 3 moles of ions, two chloride ions and one complex ion. In this case, we see formation of 4 moles of ions, 3 chloride ions and one complex ion. So 4 moles of ions will be formed in this case. And that is what we see, and we see the formation, the 3 chloride ions which are there, which are as a counter ions, will now be precipitated, as well as the number of ions, as I said, is more, so the conductivity will also be there. So the compounds are formulated based on this idea as shown in this table. So yellow compound that you can see, its structure will be CO NH3 whole 6, 3 plus charge and 3 Cl minus. This is what I said. And then the purple complex, this purple complex, this COCl with the molecular formula COCl3 5NH3, and it will form this COCl NH3 5, then 2 plus charge will be there on this complex ion and 2 Cl minus. And in this case, green and violet complexes, so two chloride ions will be in this coordination sphere of the coordination entity, and two chloride ions, one ammonia, four ammonia molecules. And so what we see, the two chloride ions are already there in this coordination sphere, and the cobalt has plus 3 charge. So now the net charge on this complex ion will be only plus 1, because the cobalt has plus 3 charge on it. And so plus, so we need only one chloride ion as a counter ion, and so this one chloride ion is there. So what we see, the solution conductivity correspond to 1 is to 3 electrolytes. So 1 is to 3 electrolytes, one can say, and this is what I think I have already explained. So here the atom within the square brackets form a single entity. So they all the atoms within this square bracket they form single entity, and that is what we call the complex ion entity that does not dissociate under the reaction conditions, and this entity does not dissociate under the reaction conditions. The reaction when it reacts with AgNO3 or when the dissolution of this complex happens in water or even during the conductor a metric or even the conductance measurement and so on. So Werner proposed the term secondary valency for the number of groups bound directly to the metal ion. So the number of groups which are directly bound to the metal ions are called the secondary valency. The secondary valency I have already explained, and now they are called the coordination number. In each of these complex examples, the secondary valencies are 6. So if you look at the example, the secondary valency is 6 in each of these examples. 2 plus 4, 2 plus 4, 1 plus 5, and the 6 directly. And so the coordination number is also 6. Werner further postulated the octahedral, tetrahedral, and square planar geometries shapes and more are more common in coordination compounds of transition metals. So later on, he also talked about the geometry of the transition metal complexes, and he said that mostly the octahedral, tetrahedral, and square planar geometries are found in the coordination complexes. And so he does a rigorous and very systematic study of coordination complexes. And at that time, when the science and this kind of detection techniques are in just they are not so developed now. We know there are many spectroscopic techniques using which you can find you can just solve you can exactly you can solve the structure of any compound, or those things were not there initially at that time, at the time when Werner did his experiment and proposed his theory. And so based on all the different kind of techniques that you can see here, two kinds of experiments: formation of precipitate and the conductance measurement. These two things you can find certain, and you can reach to certain conclusion that these things are there, and that those things are even still found to be the they are still found to be correct. So note here that the last two compounds in the table have identical empirical formula. As I said, that they have identical empirical formula, COCl3,4NH3, but distinct properties. They have different colors, distinct properties. Such compounds are termed isomers. This thing I have just explained earlier. For example, Werner further postulated that octahedral, tetrahedral, and square geometrical shapes are more common in coordination compounds of transition metals. And for example, if you look this hexaamino cobalt complex, this the 3Cl minus ion, this is octahedral, this is also octahedral, this is also octahedral. All the complexes are octahedral entities. In all the examples you can see they are octahedral. While NiCO4 is tetrahedral in shape under so it's a tetrahedral geometry. However, PtCl4 2 minus. If the secondary valency of this PtCl4 is also 4, or the coordination number of platinum in this case is also 4, but it forms a square planar complex here. In this case, also we see the coordination number or the secondary valency is 4 only, but it forms tetrahedral complex, or the shape of this complex or the geometry of this complex is tetrahedral. So these things have already been proposed by Werner. So let us look into this question, and after this I'll just stop this lecture and we'll see other parts later on, some common definitions and other things in details in the next lecture. So based on the following observations made with aqueous solution, assign secondary valencies to metals in the following compounds. So based on this thing, we have to find out what will be the secondary valency of the complexes in this all of the compounds that are found here with the empirical or the molecular formula. So the formula is molecular formula is given, and the moles of AgCl precipitated per molecule per mole of the compound with excess of AgNO3. So you add excess of AgNO3, enough amount of AgNO3 or more than enough of AgNO3, and you see how many moles of AgCl is formed. So if you see PdCl2,4NH3, and it what we see experimentally that only 2 moles of AgCl is formed per mole of this compound. It means both the Cl2 minus ions are available now, and they are out of the coordination sphere or the coordination entity. It means they are there as a counter ion. So the structure of the complex will be PdNH3 whole 4, and this forms the coordination complex, and it will have plus 2 charge on it, and so then 2 Cl minus ions as a counter ion. and those two Cl minus ions will now on dissolution in water, it will be ionized, so two Cl minus ions will be there, and those ions will now react with the Ag plus ions of HCl3 to form two moles of AgCl precipitate. Now the second structure, NiCl2 6H2. It what we see also in this case as well, 2 moles of AgCl is precipitated. It again means that only two chloride ions are there, and we see 2 moles of AgCl per mole of this compound. It means both the chloride ions are out of the coordination sphere. And if they are out of the coordination sphere, it means only 6 water molecules will be inside the coordination sphere, and so the secondary valency or the coordination number of nickel will be 6 in this complex. In this complex, as I said, it will be PdNH3 whole 4 means that in the coordination sphere, 4 ammonia molecules are complex with palladium, so which coordinate secondary valency is 4 or the coordination number of palladium is 4. In this case, what we see the 0 moles of AgCl is formed or the precipitated per mole of this. It means all the 4 chloride ions are here and 2 chloride ions here. They are inside the coordination sphere. And if everything inside the coordination sphere, the chloride ions are not outside of the coordination sphere, it means, what does it mean? It means the coordination, everything, all the chloride ions are inside the coordination sphere. And the structure of this complex one can write as PTCl6 and PTCl6, and we see 2H plus ions are also here. So it will actually be H2PTCl6 and H2P. It means the complex ion of the coordination sphere will contain PTCl6 and two negative charges will be on this coordination sphere, and so on those two negative charges will be balanced by H2H plus ions on the proton, two protons. So the coordination number of platinum in this case will be 6. In the next example, in the fourth, COCl3 4NH3, 1 mole of Cl is of AgCl is precipitated when excess of Ag3 is used for 1 mole of this complex. It means only one chloride ion is outside the coordination sphere and two chloride ions are inside the coordination sphere. And so chloride ions inside coordination sphere and 4 ammonia molecules will also be inside coordination sphere. So the secondary valency or the coordination number in the case of this complex will be 6. The next case, if you look at the PTCl2 2NH3, so we see again there is no formation of HCl in this case. It means AgCl in this case. It means both the chloride ions are inside the coordination sphere. They are very strongly bound to platinum and they are non-ionizable. And 2 ammonia molecules, they are also very strongly bound to the platinum and they are inside the coordination sphere. So total 4 chemical moieties are there inside the coordination sphere, binding directly to platinum, and so the coordination number or the secondary valency of this the platinum in this complex will be 4. 2 here and 2 here, 4. Here I'll stop this lecture and we will see other things, other important points, particularly some important terms in next class and some other important points as well in our next class.